Hi everybody, welcome back once again to this channel. Thank you very much for joining us once again. I hope you really wrote your paper 1 mathematics 2024 exam very well, and a lot of people have indicated that the paper was quite fair. It was quite fairly easy, so it means that your paper 2 might be a bit, just a bit challenging. We don't know, maybe it will be like paper 1 fair, but we need to prepare, right? So I have this interesting question really, and as you know, we are still revising the 2024 trial exam, and this is quite an interesting question from the Northwest Province under Euclidean geometry. We are really interested really in 10.2, quite a very tricky question, but very exciting at the same time. So guys, if you're new to the channel, please make sure you've subscribed. Just turn on that notification bell so that you can be notified every time when we upload a new session, also when we communicate through the community of this channel, so that you can get that notification. All right, without wasting any time, let's get into it. Okay, question 10. It says in the diagram, D is the center of the circle. Let me just indicate this with a dot there to show it's the center of the circle. BF is the tangent that touches the circle at B, and we can see it's drawn there. C lies on the circle to form chords AC and BC, and D is joined with F, and BE is equals to DE. All these are represented in your diagram. Okay, so 10.1, it says prove that angle C is equals to angle ABF. Where is angle C? Here's angle C, and here we have angle ABF, right? So prove that they are equal. How do I prove that angles are equal? Always, guys, if you have to prove that these two angles are equal, what you do is you check what this angle is equals to, right? The first one, then you check what the second angle is equals to. Okay, then you basically find they're equals to the same thing, then you can conclude they're equal because both of them are equals to the same thing. Okay, so to answer this question 10.1.1, we're gonna check what is angle C equals to. Okay, so you can see that AB is a diameter of a circle, and it's subtending an angle at the circumference, which is angle C. We do know that this angle must be what? 90 degrees, because it's angle in a semicircle. Okay, so angle C is equals to 90 degrees because angle in what? In semicircle. Okay, or angle subtended by diameter. Okay, so let's check what angle ABF is equals to. Okay, ABF, it's here. So if you check this angle, it's between a tangent BF, because we were told BF is a tangent and we can see it, and a radius DB. Can you see? We do know that radius will always be what? Perpendicular to tangent. It means that our angle ABF is also equals to 90, because radius is perpendicular to what? To tangent. Can you see now that we can now conclude that angle C is equals to angle ABF, because why? Both of them are equals to the same angle, which is 90 degrees. Then you have proven. Okay, let's go to 10.1.2 now. So 10.1.2, it says prove that DF times BC is equals to AB times BD. Okay, so you can see that this what we are given, that equation there, it's quite familiar, because we do know that if we prove similarity between two triangles, we can then move to proportionality. Then from proportionality, if you cross multiply, you can get something like that, right? So what do I do if I'm given such kind of a question? It's I identify two triangles using the letters that I used in that equation, and I'm gonna prove similarity. Then from similarity, I can then move to what? To proportionality. Okay, not necessarily proportionality. From similarity, we can move to proportionality. I mean, yeah, equal ratios between the side. Okay, then from there you can just cross multiply and show them that, right? So our task really is to identify two triangles using the letters of this, right? So let's start here. GFB. If you check, is it a triangle? Let me highlight. D is there. let me highlight this D, black color, let me use green. D is there, F is there, and B is there. It's a triangle. Can you see? We have that triangle. Great. So I have the first triangle. I'm just gonna say triangle DFB. Okay, let's identify another one. So this side maybe ABB. ABB won't be a triangle because you are repeating the letter. ABD, what about ABD? ABD, it's also that straight line, so it's not a triangle. So let's perhaps try ABC, right? If you check ABC, let me highlight this. It's a triangle. I can see it. It's sorry about this. It's ABC. Can you see? So this is a triangle. Okay. So what do I do? I'm just gonna go and prove similarity between these two triangles, right? So I'm saying in triangle DFB and triangle ABC, I have to just identify two angles that are equal between the two, right? Obviously, from the previous question, you can see that angle C in this triangle ABC is the same as angle what? Angle DBF in that other triangle. Okay, so I can see that in this small triangle in green, angle DBF is the same as what? As angle C in triangle ABC. Okay, because we have actually proven it above in the previous question. Okay, or you can say both of them are equals to 90 if you want. Then let's get the second angle that is equal. Okay, to get the second angle, if you come and check something here, oh, I just deleted this, let me rewrite it. This must be in orange, please, like this. So if you check something, we are given that BE is equals to DE. Can you see? What do we know if two sides are equal? So BE, that portion is equals to this. Okay, the two are equal, the sides are equal, they've indicated with that. So we can also see an isosceles, meaning angle D2 will be the same as angle what? Angle B2. Can you see? So because of equal sides, equal sides opposite equal angles as well, right, in that isosceles triangle. But you can see these are angles inside the two triangle, the green one. Can you see that D2, it's on the green green triangle, the smaller one, right, that we are trying to prove similarity. So we can just basically say angle D2, oh, let me use this, angle D2 in this triangle DFB is equals to angle B2. Can you see that B2, it's actually in the orange one here, right? You can see B2 there, it's on the orange one. So the two are equal. You start with what is equal, right? A lot of people confuse this reason. You find they're saying opposite angle equal side, side opposite equal angles, like that, right? So basically here you start with what is equal. What was equal was the sides, right? So you say equal what? Equal sides, opposite equal what? Angles. Okay, equal sides, opposite equal angles. So we are saying if the sides are equal, even the opposite angles are equal. Okay, so once you just get the two things, then you are done, right? You don't you can just write the third angle. You can check which angle is left here. You have used BD, you are left with F, right? Angle F here, you can just come and check the third angle of this triangle, angle F. This side we have used C, we have used B, so with angle A, so you just say third angle of what? Of triangle. Okay, they are equal because they are third angles. Therefore, we can conclude triangle DFB. Basically, when you conclude here, let's be careful. You conclude according to the angles that are equal, right? Just keep that format. and that will help you to have a correct ratio. Okay, so we are saying triangle BDF. It's actually similar, right? It's similar to triangle what? To triangle CBA. Why? By angle. Okay, so we have now proven similarity. After proving similarity, you can go to what? To proportionality. Okay, you can go to proportionality. So now that we know that triangle BDF is similar to triangle CBA, we can then move to proportionality to say BD over what? Over CB. BD over CB will be equals to what? DF over what? Over BA, right? Which is also equals to what? BF over CA. Can you see? CA. Why are we saying these are equal? Because the two triangles are what? Are similar from similarity. Okay, we can deduce that. Because from similarity, we can move to proportionality. Then you just check what you have to prove here. There's DF and BC, right? DF is there, BC is there, AB is there, and what? And BD. So we can just equate these two, right? And ignore the other one, the third one. Okay, so we can just equate the two. Then you cross multiply, it will be what? BD times BA is equals to CB times DF. Okay, so which is basically the same thing as you have your BC and DF there is equals to AB times BD. Okay, so we have managed to prove that. Let's quickly go to 10.1.3 now. So 10.1.3 says prove that E is the midpoint of the circle that passes through the point DBF. Okay, prove that E will be a midpoint of a circle that will pass through these points D, B, and F. Okay, let me just draw some small circle there. So they are saying prove that E will be at the midpoint, right, of the circle that is passing through this. So it's like E is the center of this other smaller circle. Okay, so if the center or it's the midpoint of this circle that will pass through DBF, which I've shown you in red, maybe let me use a different color so that you can clearly see this, right? This new circle that will pass through these points. Yeah, there is it. So we want to prove that E is at the midpoint, it's at the center. Okay, so basically to prove that, we can just basically prove that this line EF, right, it's actually equals to what? Is equals to EB, because we know that radii must be equal. So if that line is equals to, then we can conclude that actually it's at the center. Okay, that's the idea really. So you ask yourself, how can you prove that line? So we are saying we are required to prove, so for us to answer this question, I have to prove that maybe EB is equals to EF, right? Those two lines are equal. Then I can conclude it's a radii. Then, you know, we can conclude that that is at the midpoint. All right. So how can I prove the two lines are equals? I check the angles, right? In this triangle, let me just highlight it for you so that you see in this triangle here. I'm just gonna look at the angles, right? Angle B3 and angle F to prove that are they equal. Okay, so I'm saying if I manage to prove that angle B3 is equals to angle F, then I can conclude that indeed the two lines are equal, because it will be forming an isosceles, right? And the two sides will then be equal. Okay, so let's go and prove. So to prove that the two angles are equal, I check what is angle B3 is equals to, right? Angle B3 here is an angle between a tangent, right, and a what? And a chord of the bigger circle. So that angle there, obviously it will be equals to angle A, right, by what? By tan chord. So angle B3 will be equals to angle A by tan chord theorem that says angle between tangent and chord equals to angle subtended by the two other chords at the circumference. Okay, so then I check what is angle F equals to. We have already shown that angle F and A are equal because those were third angles of triangle in the previous one, right, when we were proving similarity there. So we can just say proven above. Then therefore we can deduce that angle B3 now it's equals to angle F because both of them are equals to what? Angle A. Okay, so now we have just proven that these two angles are what? Are equal. So if they are equal, what can we conclude? We can conclude that line EB will be equals to line what? Line EF. Why are we saying they are equal? Because we are saying angles that are opposite are equal. Opposite side, right? Because of what? Sorry about that. Angles opposite equal what? Equal sides. Our deduction is that the sides are equal because the angle that are opposite are equal. This means that the sides are also equal. Okay, so because we have just proven that EB is equals to EF, we can also deduce that EB is equals to EF, and EF, you know, EB is equals to EF, and we're given that BE is also equals to DE. Can you see? Which is the same as what? As DE. So they are equal. Those like are radius, right? Therefore, because we are saying all this side, let me just show you here. Because we are saying all these are equal, we can deduce that E what? E is at the center. Not at the center, at the midpoint, right? At the midpoint of the line that passes through that, because what? The radii, they are what? Are equal. Okay, so that's the idea really. Let's quickly go to 10.2, which is our main focus in this paper. All right, 10.2, it says prove that 1 over BC squared minus AB squared is equals to negative AB times FB divided by EF times AC exponent 3. All right, so you can see that this is quite a complicated equation, right? And you might be asking yourself, where do I start? How do I prove such kind of things, right? So basically, to solve this, we have to use our answers to the previous questions, right? You know, because these are ratios. There are some ratios of proportionality there that we can identify, such as like side AC, right? Remember in the previous proportionality, after proving that the two triangles were similar, we can have AC there. BF is there, FB, you know, there is it as well, and you can also identify some of those. AD, do we have AD? I think we don't have AD there, but you have your AB, which is also part of this. Okay, so you can see that basically we can start from that proportionality. Okay, then we can go and see how far we can go with that. Okay, so I'm just gonna start with the proportionality to say we do understand that DF, right, DF over AB, right, it's basically the same as BF over CA. And why am I choosing these two? Is because I can see AC, I see AC in what I have to prove. I can see FB, I see FB in what I have to prove. I can see AB and I see AB in what I have to prove. The only thing that is not there is DF, right? So perhaps we'll need to know what does DF equals to. So I'm saying those two are equal because I've already proven similarity there. Okay, sometimes you just need to show them it's because these two triangles are similar, but you can just say from what? From similarity, because from similarity we can go to proportionality. Okay, so the only issue I have is it's with DF here. I don't have DF in what I have to prove. It means let's go and check what DF is equals to. Okay, so if you check DF, it's this line here. From here to here, right? Remember in the previous question we just proven that this line is the same as this, which is the same as this. Okay, so you can see that DF is basically the same as DE, Perhaps let me write this. We are saying but df is equals to de plus ef, right? But the two are equal. Okay, so I'm just saying df is like that side plus that one, right? But I know here that the two are equal, right? De, but I know that let me say, but again, de is equals to what? ef. I've just proven it above in 10.1.3, right? Proven above. Okay, so what I can do is I can go and substitute df with something related to ef, because I can see there's also ef there, right? That needs to be there. So I'm just gonna say df will be equals to what? Because the two are equal, de is the same as ef, so it will be ef plus ef, which will be 2ef, right? 2ef. So when there is df, I can just go and substitute by what? By 2ef. Okay, so I can have 2ef over AB is equals to BF over what? Over CA. All right. Okay, so from that moment you can see that FB, we have it on top here. I can just write it as FB, right? FB, so that you clearly see this one is AC, right? Can just write it like that, and EF there, right? I have FB, AC, AB there, right? So basically what I can do at this point, I can try to have everything that I have that side, right? So perhaps let's go and check what does AB equals to, right? If you check, AB is the diameter, so this is the center, so you know that AB will be the same as AD time plus what? Plus dB, right? So basically I can try to express it in the form of AD, right? Because the two are equal, because they are equal radii, right? So I can also say, but I also know from this moment that my AB, the whole of AB is equals to AD plus what? DB. Can you see there? But I know that AD and DB are what? Are equal. Okay, because they are what? Equal what? Equal radii, right? They are radiuses, so the radiuses are equal. Okay, so basically from this step I can express AB in the form of what? AD, because I can also identify AD there, right? So let's go and express AD in the form of AB. I'm just gonna delete some of the things here so that we create some space. So now I'm saying that AB will be equals to AD plus, where there is DB is the same as AD, I can replace with AD, so it's AD plus AD, which is also what's 2AD. All right, so after getting this, I can go back to my proportionality here and substitute. Okay, I can say therefore I now have 2EF over AB is the same as 2AD, which is the same as what? FB over what? Over AC. Can you see? So from this moment you can see we are heading somewhere. 2 over 2 will cancel, right? So the 2 will go away. Then check something. How can I get EFAC ADFB? I can just cross multiply, right? Because if you cross multiply like that, you'll get EFAC and ADFB, right? But rather than cross multiplying, we can also choose to just multiply by the reciprocal, right? So that the other one goes that side. So I can multiply here by what? AD over EF. What I do this side, I must do it this side. I multiply with AD over what? Over EF, right? So AD and AD will cancel, EF and EF will cancel. I'm left with 1 is equals to, I have FB times AD. Can you see? So I have like AD times FB divided by what? EF times what? Times AC. Can you see that we have something similar to what we have to prove there? Right? We are just left now to show that this side, also this side, will be give us something like that, right? Now this was quite a tricky question, really, and I do understand perhaps the frustration maybe at this moment, because there's a lot happening, right? But the idea is that I'm trying to get this side that I had, and we have now successfully gotten it. We're just left with a negative. Perhaps it will come when we go and explore how to get BC squared over AB squared, right? My concern now is that, okay, I have ADFB, great. EF is there, but my AC here is not to the exponent of 3, it's just AC. Then I ask myself, how can I get this to be AC exponent of 3? That's where manipulation comes, and that's where the trickiness of this question is, right? So we have 1 is equals to AD times FB divided by EF times what? AC. I'm asking myself, how can I make AC to be exponent of 3, right? By multiplying by 1 over what? AC squared. So that AC squared times this will be AC exponent of 3. But what I do on the left, on the right, must also be done on the what? On the left. Also here I'll multiply with 1 over AC squared, right? So here I have 1 over AC squared is equals to AD times FB over EF times AC exponent of 3, because the 2 when they multiply there will give you AC exponent of 3. Then you can see I now have that part. I'm just left with the negative, which will perhaps comes after we solve for AC squared. Okay, let me just create some space now. Okay, now I can see that I'm just left to solve this side to check what does AC squared equals to, because in what we have to prove we don't have AC squared there, right? So I go and check what does AC squared is equals to, right? So if you check this triangle ABC here, we have a 90 degrees there because it's an angle in a semicircle, so it's a right angle triangle, and you know that by Pythagoras, right? So I can just say, but from Pythagoras, I know that AB squared, the hypotenuse squared, will be the same as the sum of the other two sides squared. AC squared plus what? Plus BC squared. And this is coming from what? Pythagoras, right? So if I solve for AC squared, you'll agree that it will be equal to what? AB squared minus what? Minus BC squared, right? It will be the same as that. And you can see it's something close to this. It's not yet like that. So if I remove a negative there, right, so that BC is positive, so you'll have your BC now, which is now what? Positive minus what? AB squared. Can you see where the negative now is going to help us when we divide both sides, and we'll finally prove, right? But some people might prefer to do it differently, right? To just make AC negative, something like that. So you might prefer to do this, or someone can say, okay, let's just take AB squared this side and AC that side, right? So if I take AC squared, that side will be negative AC squared is equals to this side we have BC squared minus what? Minus AB squared. Can you see? It's BC squared minus AB squared, which is part of what we have to prove there, right? So it means that my AC is negative. I can just divide both sides by what? By negative. Can you see? So something like that, or you keep it as negative AC squared, right? But we can just, for the sake of it being AC, we divide by -1. Then now finally you just go and substitute. So when there is AC squared, I'm gonna put what? I'm gonna put this. So it's negative there, right? So I'm just gonna put BC squared minus AB squared, this is divided by -1, right? That is where AC is. This is equals to AD times FB divided by EF times AC exponent 3. Then I can cross multiply, the negative can go that side, right? Because it's negative, so I can just take it and cross multiply with that side. So finally I'll have 1 over BC squared minus AB squared will be equals to negative AD times FB divided by EF times what? AC exponent 3, and we have finally proven that. Okay, it was quite a bit messy, long, and all that, but the key idea, guys, is that you had to think, go back to your proportionality that you proven above. You know, if a question asks you that prove that the two triangles are similar, then you know that from similarity you can go to proportionality. So basically you check in your proportionality what is there to be proved, then you just tick there, you tick there, then you can see which ones to equate and which ones to it's not important. Then you go back and look at your properties, then you finally solve it. Okay, so this was also quite challenging because you had to also multiply by 1 over AC squared there, because there was no way you could get AC exponent 3. So you should have those manipulative skills as well. Okay guys, I hope you find this helpful. Don't forget to like, share, comment, and subscribe. See you soon. Bye.